let yourself settle in now. Find that spot where your body naturally wants to rest, where the day's tension begins to melt away like morning frost under gentle sunlight. Take a slow breath, deep and easy, feeling the cool air enter and the warm air leave, carrying with it any worries or thoughts that no longer serve you tonight. Tonight, we're embarking on a journey to a distant world, but you don't need to move a muscle. Just allow the story to unfold around you, painting pictures in your mind of red deserts, distant horizons, and the profound questions that arise when we contemplate leaving Earth forever. Before we drift into the cosmos together, I want to thank you for being here with The Science Pillow, where we merge scientific curiosity with relaxation. If you enjoy these journeys through space and science, please consider subscribing to the channel and giving this video a like. It helps others find these peaceful explorations and allows us to create more content for your restful evenings. Your support means everything to this channel and to the community we're building together, one curious mind at a time. Now, breathe again. Let your eyes close if they haven't already, or let them rest softly on some distant point. We're going to explore one of the most profound truths about the future of human space exploration. A truth that challenges our deepest assumptions about adventure, exploration, and what it means to leave home. The journey to Mars, that gleaming red beacon in our night sky, may very well be a one-way trip. Not because we lack the ambition to return, but because the physics, biology, and sheer reality of interplanetary travel create barriers that transform a round-trip mission into something far more final than we typically acknowledge. So relax into this exploration, and let's understand together why the path to Mars may only lead in one direction. Section 1. The Dream of Mars. For as long as humans have gazed upward at the night sky, Mars has captured our imagination. There, suspended among the stars, hangs a world that glows with a rusty, reddish hue, a color that ancient civilizations associated with blood and war. The Egyptians called it Herdesher, meaning the Red One. The Romans named it after their god of war. For millennia, this wandering light in the heavens sparked questions. What is that distant world? Could anything live there? Could we ever reach it? In the late 19th century, astronomers peering through increasingly powerful telescopes thought they saw canals crisscrossing the Martian surface. Italian astronomer Giovanni Schiaparelli described channels, or canali in Italian, which were mistranslated as canals, implying artificial construction. American astronomer Percival Lowell became convinced that these were the engineering works of an advanced Martian civilization, desperately channeling water from the polar ice caps to irrigate their dying world. Though later observations proved these canals to be optical illusions, the dream of life on Mars had taken root in human consciousness. The 20th century brought our first real encounters with Mars. In 1965, NASA's Mariner 4 flew past Mars and sent back the first close-up images of another planet. Instead of canals and cities, the photographs revealed a barren, cratered landscape that looked more like the moon than the vibrant world of imagination. The atmosphere was discovered to be incredibly thin, composed mostly of carbon dioxide, with surface pressures less than 1% of Earth's. Temperatures ranged from a relatively balmy 20 degrees Celsius at the equator during summer to a bone-chilling 125 degrees below zero at the poles in winter. Yet each new discovery, rather than diminishing our fascination, seemed to deepen it. The Viking landers of 1976 tested Martian soil for signs of life, producing ambiguous results that scientists still debate today. Mars Pathfinder and its Sojourner rover in 1997 showed us a world of rocks and rust-colored dust stretching to distant horizons. The twin rovers, Spirit and Opportunity, which landed in 2004, found compelling evidence that liquid water once flowed across the Martian surface. Minerals that only form in the presence of water, dried-up river channels, and what appeared to be ancient lake beds told a story of a Mars that was once warmer, wetter, and perhaps more hospitable to life. This transformed Mars from a dead world into a world that had died, or at least dramatically changed. Billions of years ago, Mars likely had a thicker atmosphere, liquid water on its surface, and conditions that might have supported life. Understanding what happened to Mars, why it lost its atmosphere and its water, why it became the cold desert we see today, might help us understand the future fate of Earth itself. The scientific value alone justifies the immense effort and cost of exploration. But the dream of Mars extends beyond pure science. In recent decades, visionaries and space agencies have begun seriously discussing not just visiting Mars, but actually establishing a permanent human presence there. The logic is compelling, even urgent to some. Earth, for all its beauty and abundance, presents certain existential risks. An asteroid impact, nuclear war, climate catastrophe, or some other global catastrophe could threaten human civilization or even human existence. By becoming a multiplanetary species, by establishing self-sustaining colonies on other worlds, we create a backup for humanity. We ensure that no single event on Earth could extinguish the light of human consciousness in the universe. Mars is the logical choice for this endeavor. Venus, though closer and similar in size to Earth, has surface temperatures hot enough to melt lead and atmospheric pressure 90 times greater than Earth's, crushing conditions that make even brief visits extraordinarily difficult. Mercury lacks an atmosphere entirely and experiences temperature swings of 600 degrees between day and night. The gas giants Jupiter, Saturn, Uranus, and Neptune have no solid surface to stand on. The moons of these planets, particularly Jupiter's Europa and Saturn's Titan, present intriguing possibilities for exploration, but they're much farther away than Mars and present their own unique challenges. Mars, by comparison, offers several advantages. It's relatively close, about 225 million kilometers from Earth at its nearest approach, a journey of 6 to 9 months with current propulsion technology. It has a day, called a sol, that lasts 24 hours and 39 minutes, nearly identical to Earth's, which would make it easier for human circadian rhythms to adapt. It has polar ice caps made of water ice and frozen carbon dioxide. It has seasons, though they're about twice as long as Earth's, because Mars takes 687 Earth days to orbit the Sun. The gravity, while only 38% of Earth's, is still substantial enough that humans can walk and function, unlike the Moon's meager 16%. Most importantly, Mars has resources that could support human life with the right technology. Organizations like NASA, the European Space Agency, China's space program, and private companies like SpaceX have all developed plans for Mars missions. Elon Musk has made it SpaceX's explicit goal to establish a self-sustaining city on Mars within our lifetimes. NASA's Moon to Mars initiative aims to use lessons learned from returning to the Moon to prepare for eventual crewed missions to Mars, potentially in the 2030s or 2040s. The vision is inspiring. Humans walking on another planet, establishing habitats, conducting research, maybe even raising families under alien skies. But here's what all these plans must ultimately confront: the immense difficulty, perhaps the impossibility, of bringing those first. Mars explorers home again. When we talk about Mars missions in excited, optimistic terms, we often gloss over an uncomfortable truth. The combination of factors that make Mars exploration so challenging: radiation exposure, fuel requirements, environmental hazards, physiological changes, and psychological strain, don't just make the mission difficult. They create a situation where the most practical, perhaps the only realistic approach, is a one-way mission. The first humans to set foot on Mars might need to accept that Mars is where they'll stay, not for a few months or years, but for the rest of their lives. This isn't a failure of engineering or imagination. It's a consequence of physics and biology operating at the extreme limits of what human technology and human bodies can endure. To understand why requires us to examine each of these factors in detail, to see how they combine and compound to create a situation where the return journey becomes exponentially more difficult than the outbound trip. The dream of Mars is still alive and worth pursuing, but we need to be honest about what it entails. Let's explore, with open eyes and clear minds, why the journey to Mars may only go one direction. Section 2. The Radiation Gauntlet. Imagine yourself standing outside on a beautiful spring day, feeling the warmth of the sun on your face. That warmth, that light, represents just a tiny fraction of the energy the sun pours into space every second. Most of that energy is visible light and infrared heat, relatively benign forms of electromagnetic radiation. But the sun also produces much more dangerous radiation: ultraviolet light, X-rays, and energetic particles traveling at substantial fractions of the speed of light. Under normal circumstances on Earth, you never have to worry about this deadly radiation. You're protected by an invisible shield so effective that you probably never even think about it. This shield has two components. First is Earth's magnetic field, generated by the churning molten iron in our planet's core. This magnetic field extends tens of thousands of kilometers into space, forming a bubble called the magnetosphere that deflects most of the charged particles streaming from the sun, called the solar wind. You can actually see this protection at work during auroras, when some solar particles do make it through near the poles and collide with our atmosphere, creating those dancing curtains of green and red light. The second component of our shield is the atmosphere itself, a blanket of gas about 100 kilometers thick that absorbs most of the harmful ultraviolet light, X-rays, and any particles that make it through the magnetic field. Together, these shields reduce the radiation reaching Earth's surface to levels that life can tolerate and even thrive under. We've evolved under this protection. Our cells, our DNA, our entire biology assumes this level of radiation shielding. It's so fundamental to life on Earth that we rarely consider it, like the oxygen we breathe, or the gravity that holds us to the ground. Now, picture yourself aboard a spacecraft heading to Mars. You've left Earth's magnetic field behind. You're traveling through interplanetary space in a thin-walled metal can. There's no atmosphere to shield you, just the walls of your spacecraft and whatever additional shielding engineers could squeeze into the design without making the vehicle too heavy to launch. Every second of every day, you're being bombarded by radiation levels that would be lethal on Earth. This radiation comes from two primary sources. The first is galactic cosmic rays, or GCRs. These are atomic nuclei, mainly protons and heavier elements, that have been accelerated to nearly the speed of light by supernova explosions, spinning neutron stars, and other violent events scattered across our galaxy. They're incredibly energetic, capable of passing through the hull of a spacecraft, through your spacesuit, through your body, ripping through your cells and damaging DNA along the way. One radiation researcher described it vividly. They rip through you like you're cellophane. The second source is solar particle events, sometimes called solar storms. The sun isn't a steady, constant source of energy. Its surface roils with magnetic activity, forming sunspots, solar flares, and massive eruptions called coronal mass ejections. When these events occur, they can accelerate enormous numbers of particles, mostly protons, to very high energies and send them streaming through space. If one of these particle storms hits your spacecraft during the journey to Mars, the radiation dose can spike dramatically in just hours or days. Scientists working with the European Space Agency's ExoMars Trace Gas Orbiter, which traveled to Mars and has been orbiting there since 2016, have been measuring radiation levels throughout the journey and in Martian orbit. Their findings are sobering. They determined that astronauts making the same trip would receive approximately 60% of their maximum recommended career radiation dose just from the round-trip journey itself, before spending any time on the Martian surface. Let's put that in perspective. Career radiation limits for astronauts vary based on age and sex, ranging from 1 sievert for a 25-year-old woman to 4 sieverts for a 55-year-old man. A sievert is a measure of radiation dose that accounts for both the amount of energy deposited in tissue and the biological damage that energy causes. For comparison, a typical chest X-ray exposes you to about 0.1 millisieverts, or 1/10,000th of a sievert. The annual radiation dose that workers in nuclear power plants are allowed to receive is 50 millisieverts, or 0.05 sieverts per year. Astronauts on the International Space Station, orbiting about 400 kilometers above Earth's surface, still have some protection from Earth's magnetic field. They receive roughly half the radiation they would get in deep space, approximately 150 millisieverts per year. That's still significant, about 3 times what nuclear workers can receive, but it's manageable for missions of 6 months to a year. But the journey to Mars takes you far beyond Earth's protective embrace. The radiation during the trip to Mars would be several hundred times higher than what you'd experience on Earth's surface over the same period. One physicist studying cosmic radiation explained that just 1 day in space equals the radiation you'd receive on Earth over an entire year. A trip to Mars would be like undergoing roughly 20 to 30 KT scans, according to some estimates. That's about 15 times the annual radiation limit for workers at nuclear power plants. What does this radiation do to the human body? The effects operate on multiple timescales. In the short term, very high doses of radiation can cause acute radiation sickness, with symptoms including nausea, vomiting, fatigue, and damage to the immune system. The doses during a Mars journey aren't quite high enough to cause these immediate symptoms under normal conditions, though a major solar particle event could potentially push doses into this range if the spacecraft doesn't have adequate shielding. The real danger is cumulative and long-term. Radiation damages DNA by breaking the chemical bonds that hold the DNA molecule together. Our cells have repair mechanisms to fix this damage, but they're not perfect. If the damage is severe enough or occurs faster than cells can repair it, mutations can accumulate. These mutations can cause cells to die, to malfunction, or in the worst case, to become cancerous. Cancer is the most well-known long-term risk of radiation exposure. The increased radiation on a Mars mission would significantly elevate the astronaut's lifetime cancer risk. But cancer isn't the only concern. Research has revealed that radiation can damage the cardiovascular system, increasing the risk of heart disease and stroke. Studies of astronauts who traveled beyond Earth's magnetosphere during the Apollo missions showed higher rates of cardiovascular disease compared to astronauts who stayed in low Earth orbit or never flew in space. Recent research has identified another alarming effect: radiation damage to the brain and central nervous system. The high-energy particles in cosmic rays can cause inflammation in the brain, damage neurons, and impair cognitive function. Studies in animals exposed to the types of radiation found in deep space have shown changes in behavior, decreased performance on memory tasks, and alterations in the brain structures involved in learning and decision-making. Astronauts on a Mars mission might experience difficulties with memory, attention, and problem-solving, precisely the cognitive functions they'll need most for the complex tasks required to survive on Mars. The damage to the cardiovascular system and the central nervous system appears to be dose-dependent, meaning the longer you're exposed to the radiation environment of deep space, the more damage accumulates. This creates a cruel paradox: the return journey, coming after months or years on Mars where radiation exposure continues, would add to an already dangerous cumulative dose. Each additional day in the radiation environment of space or Mars increases the likelihood of developing cancer, heart disease, cognitive impairment, and other health problems later in life. Couldn't we just build better shielding? This is the obvious question, and researchers have been working on it for decades. The challenge is that shielding against cosmic rays isn't as simple as putting up a thick metal wall. In fact, some types of metal shielding can actually make the problem worse. When high-energy cosmic ray particles hit heavy metal atoms, they can create showers of secondary particles through a process called spallation. These secondary particles can be just as damaging, sometimes more so, than the original cosmic ray. The most effective shielding materials are those rich in hydrogen, because hydrogen nuclei, being single protons, are about the same size as the particles you're trying to stop. Materials like water, polyethylene plastic, and certain other hydrogen-rich compounds can reduce radiation exposure. Some proposed spacecraft designs include surrounding the crew quarters with tanks of water, which would serve double duty as both radiation shielding and a resource for drinking and growing food. But here's the problem: effective shielding is heavy. Water, polyethylene, and other hydrogen-rich materials need to be several meters thick to significantly reduce cosmic ray exposure. A spacecraft designed to carry enough shielding to reduce radiation doses to acceptable levels would be enormously massive, requiring vastly more fuel to launch from Earth and to propel through space. The mass of the shielding quickly becomes prohibitive. Some researchers have explored the possibility of creating magnetic fields around spacecraft, mimicking Earth's magnetosphere on a smaller scale. This is theoretically possible, but generating a magnetic field strong enough to deflect cosmic rays would require enormous amounts of power, far beyond what current spacecraft can generate with solar panels or even nuclear reactors. The structural requirements for creating such a field would also add significant mass to the spacecraft. While magnetic shielding remains an active area of research, it's not currently a practical solution for a near-term Mars mission. There's another radiation concern that becomes relevant once astronauts reach Mars: The planet itself offers far less protection than Earth. Mars has no global magnetic field to speak of. Billions of years ago, Mars did have a magnetic field, generated by a molten core like Earth's, but the core cooled and solidified, and the magnetic field disappeared. Without this protection, the solar wind has been gradually stripping away Mars's atmosphere for eons. The thin atmosphere that remains, less than 1% the density of Earth's, provides minimal shielding against radiation. Measurements taken by NASA's Curiosity rover on the Martian surface show that the radiation dose there is roughly half of what you'd experience in deep space. This is because Mars itself blocks radiation from below, providing some shielding, but it's still vastly higher than Earth's surface. An astronaut living on Mars would receive about 0.7 millisieverts per day, or roughly 250 millisieverts per year, about 5 times what astronauts on the International Space Station experience, and about 1,000 times what you'd receive on Earth's surface. This means that even after reaching Mars, even after establishing a habitat on the surface, the radiation exposure continues. Every day on Mars adds to the cumulative dose. Habitats would need to be heavily shielded, perhaps built underground or covered with meters of Martian soil to reduce exposure to acceptable levels. But astronauts couldn't stay inside shielded habitats all the time. They'd need to venture outside to conduct research, maintain equipment, tend to food, production systems, and perform countless other tasks necessary for survival. Each excursion would add to their radiation burden. The mathematics of radiation exposure for a Mars mission is unforgiving. The outbound journey exposes astronauts to roughly 60% of their career limit in dose. Time on the Martian surface continues to add to that total. The return journey would add another substantial dose. Depending on how long the mission lasts and how effective the radiation countermeasures are, many astronauts could exceed safe lifetime limits before they even made it home. And here's perhaps the most troubling aspect. We don't fully understand all the long-term effects of deep space radiation. Most of our knowledge about radiation effects comes from studies of people exposed to X-rays and gamma rays, like atomic bomb survivors and radiation accident victims. But cosmic radiation is different. It includes heavy ions, particles with multiple protons and neutrons, traveling at relativistic speeds. These particles interact with tissue differently than X-rays do, creating unique patterns of damage that we're only beginning to understand. One researcher studying space radiation put it bluntly. The real problem is the large uncertainty surrounding the risks. We don't understand space radiation very well, and the long-lasting effects are unknown. We're asking astronauts to accept not just known risks, but unknown ones, to venture into a radiation environment that no human has experienced for more than a few weeks at a time, to stay in that environment for months or years, all while understanding that we can't fully predict what it will do to their bodies over the course of their lifetimes. This radiation challenge doesn't make a Mars mission impossible, but it does fundamentally change the calculation. If the goal is to bring astronauts home safely after a relatively brief visit to Mars, the cumulative radiation dose becomes one of the mission's most severe constraints, limiting how long the mission can last and requiring expensive, heavy shielding that drives up costs and complexity. But if the mission is one way, if the astronauts are going to stay on Mars permanently, then the radiation dose from the return journey disappears from the equation. The cumulative dose is still a serious health concern, increasing the risk of cancer and other diseases, But it's no longer a hard limit that forces the mission to end before safe exposure limits are exceeded. The radiation gauntlet is one of the first major factors pointing toward the practical necessity of one-way Mars missions. Section 3. The fuel equation, the tyranny of the rocket. Picture in your mind a rocket standing on a launch pad, fueled and ready for liftoff. What you're looking at is, in essence, a barely controlled explosion. The vast majority of the rocket's mass, typically 70 to 80% or more, is propellant. Liquid hydrogen and oxygen, kerosene and oxygen, or some other combination of fuel and oxidizer. This propellant will be consumed in minutes during the launch, generating the tremendous thrust needed to overcome Earth's gravity and accelerate the rocket to orbital velocity. Getting to space from Earth's surface requires reaching a speed of about 7.8 kilometers per second, or roughly 28,000 kilometers per hour, to achieve low Earth orbit. To escape Earth's gravity entirely and head toward Mars requires even more velocity, about 11 kilometers per second. These speeds represent enormous amounts of kinetic energy, and achieving them requires burning enormous quantities of propellant. The relationship between the mass of propellant and the final velocity a rocket can achieve is governed by the Tsiolkovsky rocket equation, named after the pioneering Russian rocket scientist Konstantin Tsiolkovsky. This equation reveals a fundamental, unforgiving truth about space travel. Velocity increases logarithmically with the ratio of the rocket's initial mass to its final mass. In simpler terms, if you want to go faster or carry more cargo, you need exponentially more fuel. Let's make this concrete with some numbers. Current estimates suggest that for every kilogram of useful equipment or payload you want to send to Mars, you need somewhere between 7 to 11 kilograms of mass at launch from Earth. This translates to about 6 to 9 kilograms of propellant needed just to get each kilogram of payload on its way to Mars. But it gets worse. If you're not just sending that payload to Mars but also bringing it back, you need to include the mass of the return propellant in your calculations. Here's where the tyranny of the rocket equation really bites. If you want to have propellant on Mars for the return journey, that propellant has to either be manufactured on Mars using local resources, which we'll discuss later, or it has to be transported from Earth. If you're transporting propellant from Earth to Mars to use for the return trip, you have to account for something called the gear ratio. The gear ratio represents how many kilograms of propellant you need to burn to deliver 1 kilogram of propellant to your destination. For Mars, this gear ratio is approximately 226 to 1. Read that again and let it sink in. To have 1 kilogram of propellant sitting on the surface of Mars, ready to fuel a return journey, you need to burn 226 kilograms of propellant getting it there from Earth. This isn't inefficiency or waste. This is pure physics, the unavoidable consequence of the rocket equation. Let's calculate what this means for a realistic Mars return mission. NASA estimates that a Mars ascent vehicle, the rocket that would launch astronauts from the Martian surface into Mars orbit, where they could rendezvous with their Earth return spacecraft, would need approximately 30 to 33 metric tons of propellant. That's 30,000 to 33,000 kilograms. If you had to bring this propellant from Earth, you would need to burn 226 kilograms of fuel for each kilogram delivered, requiring about 6.8 to 7.5 million kilograms of propellant just to get the Mars ascent vehicle's fuel to Mars. But wait, it gets even more complicated. that 6.8 million kilograms of propellant itself has mass that needs to be lifted from Earth and accelerated toward Mars. Accounting for this in your calculations creates a recursive problem where the fuel to carry the fuel requires fuel to carry it, and so on. The numbers spiral upward rapidly. The cost implications are staggering. Estimates suggest that transporting the approximately 30 tons of methane and liquid oxygen needed to fuel a return spacecraft from Mars would cost around $8 billion. And that's just the fuel for the return leg. This doesn't include the spacecraft itself, the habitats, the life support systems, the food and water, the scientific equipment, or any of the other countless systems needed for a Mars mission. Comparison with the Apollo moon missions is instructive. The moon is much closer to Earth than Mars, requiring a journey of just 3 days instead of 6 to 9 months. The moon's gravity is only 1/6 of Earth's, compared to Mars's 3/8. This means far less fuel is needed to land on the moon and take off again. Yet, even for the relatively modest challenge of a moon landing, the Saturn V rocket that launched the Apollo missions was enormous, standing 111 meters tall and weighing about 2,970 metric tons fully fueled. Only the tiny command module, weighing about 5,800 kilograms, returned to Earth, less than 0.2% of the rocket's initial mass. Mars missions face a much harsher version of the rocket equation. The journey is longer, requiring more propellant to maintain life support systems during the cruise. The target planet is more massive, with stronger gravity that requires more fuel to escape from. The round-trip travel time, accounting for the need to wait for favorable orbital alignments between Earth and Mars, would be roughly 2 to 3 years for a traditional mission profile. Every additional day in space is another day of consumables, food, water, oxygen that needs to be carried along, adding more mass to the mission and requiring yet more fuel. Engineers have proposed various strategies to mitigate the fuel problem. One approach is to use a cycler orbit, a spacecraft that continuously travels between Earth and Mars on a carefully calculated trajectory, allowing crews to board when it passes near Earth and disembark when it passes near Mars. This eliminates the need to accelerate and decelerate the entire habitat multiple times, but it requires precise timing and doesn't solve the problem of getting crews and equipment to and from the cycler. Another approach is nuclear thermal propulsion, where a nuclear reactor heats propellant to extremely high temperatures, producing more thrust per kilogram of fuel than chemical rockets. This technology was actually developed and tested during Project Nerva in the 1960s and 1970s, demonstrating the feasibility of the concept, but political opposition to launching nuclear reactors into space has prevented its use on actual missions. The most promising approach, the one that SpaceX and NASA both plan to use, is in situ resource utilization, or ISRU. This means manufacturing the propellant for the return journey on Mars itself using Martian resources. The logic is compelling. Instead of hauling fuel from Earth at a 226 to 1 gear ratio, you produce the fuel where you need it, using resources available locally. Mars's atmosphere is 95% carbon dioxide, and water ice exists beneath the Martian surface, particularly at higher latitudes. Through a process called the Sabatier reaction, carbon dioxide can be combined with hydrogen to produce methane and water. The water can then be split into hydrogen and oxygen through electrolysis, with the hydrogen recycled back into the Sabatier process, and the oxygen stored for use as an oxidizer. The result is methane fuel and liquid oxygen, both suitable rocket propellants, produced entirely from Martian resources. NASA's MOXIE experiment, part of the Perseverance rover mission, successfully demonstrated this principle, producing small amounts of oxygen from Martian carbon dioxide. Scaling this up to produce the tons of propellant needed for a return mission is technically feasible, but requires sending significant equipment and infrastructure to Mars ahead of time. You'd need reactors to carry out the chemical processes, electrolyzers to split water, compressors, and refrigeration equipment to liquefy and store the propellants, and, most critically, a reliable power source to run everything. Likely a nuclear reactor, since solar power alone would be insufficient. Here's where the one-way nature of Mars missions becomes apparent through the fuel equation. If you're planning a return mission, you need to send all this fuel production infrastructure to Mars before the crew even launches from Earth. This infrastructure needs to operate autonomously for possibly years, producing and storing propellant, so it's ready when the crew arrives. The equipment needs to be robust enough to survive Martian conditions, dust storms, extreme temperatures, with no human maintenance. And even if everything works perfectly, you're still betting the lives of your crew on equipment that's never been fully tested in actual Martian conditions. If something goes wrong with the ISRU system, if it produces less fuel than expected, if some critical component fails, if the water, ice is deeper or harder to extract than anticipated, the crew could be stranded with no way to launch from Mars. The entire mission design becomes vastly more complex, expensive, and risky when return propulsion is part of the plan. Contrast this with a one-way mission. The astronauts still need propellant to land on Mars, to be sure, but they don't need any fuel for takeoff or return. This eliminates the need for the Mars ascent vehicle entirely, saving enormous mass and complexity. The ISRU systems can be focused on producing oxygen for breathing, water for drinking and agriculture, and other consumables for survival, which are much more modest requirements than producing tons of rocket fuel. The spacecraft that carries the crew to Mars can be optimized for a one-way trip, carrying more supplies, more scientific equipment, better radiation shielding, everything that makes the mission more likely to succeed and the crew more comfortable, because you're not constraining the mass, budget to accommodate return fuel. The mission becomes simultaneously simpler and more capable. Some mission planners have proposed compromise approaches. Send the crew on a one-way trip to Mars, but plan to manufacture enough fuel for a return journey over time, maybe years after arrival, once ISRU systems have proven themselves and accumulated sufficient propellant. This provides optionality. If the crew wants to return and the fuel is available, they can. If they decide to stay, or if fuel production falls short, the mission continues as a one-way endeavor. But even this approach faces challenges. A spacecraft sitting on Mars for years, exposed to dust, temperature cycling, and radiation, may not remain functional. The crew would need to maintain it, test it, keep it in working condition, all while conducting the science and survival tasks that are the primary mission objectives. And the psychological burden of having a return option, a way home that might or might not work, could be harder to bear than the certainty of a one-way mission where everyone has accepted from the start that Mars is their permanent home. The fuel equation, the mathematics of rocket propulsion, creates an almost insurmountable barrier to practical, affordable, sustainable round-trip Mars missions with current technology. The exponential relationship between mass and velocity means that bringing astronauts home costs vastly more than sending them out. Each kilogram of return fuel requires hundreds of kilograms to be burned getting it there. The complexity and risk of ISRU systems add further uncertainty. When you step back and look at the full picture, the fuel equation whispers a difficult truth. The most feasible path to Mars, at least with the technology available to us now and in the foreseeable future, is one way. Section 4. The Alien Environment. Close your eyes and imagine standing on the surface of Mars. Above you stretches a sky that isn't the familiar blue of Earth, but a butterscotch tan, colored by iron oxide dust that hangs perpetually in the thin atmosphere. The sun appears smaller, about 2/3 the size it appears from Earth, because Mars orbits farther from our star. The sunlight feels weaker, reaching you at only about 43% the intensity it has on Earth. When the sun sets, temperatures plummet with terrifying speed in the thin atmosphere that retains almost no heat. The environment around you is lethal in ways both obvious and subtle. Let's start with the most immediate challenge. You can't breathe. Mars's atmosphere is 95% carbon dioxide, with small amounts of nitrogen, argon, and trace gases. There's oxygen, but only about 0.13%, far too little to sustain human life. Even if the composition were right, the pressure is wrong. The average surface pressure on Mars is about 600 pascals, roughly 0.6% of Earth's sea level pressure. To put this in perspective, imagine climbing to the summit of Mount Everest, where the air pressure is about 1/3 of sea level. Now imagine going almost 70 times higher, to an altitude of about 45 kilometers above Earth's surface. That's the equivalent pressure of standing on Mars's surface. At this pressure, water boils at just 2 degrees Celsius. The liquids in your body would begin to vaporize. Your lungs couldn't function. Without a pressure suit providing oxygen and maintaining adequate pressure around your body, you would lose consciousness in about 15 seconds and die within 2 minutes. But let's say you're wearing a spacesuit, providing breathable air and pressure. The temperature is your next challenge. Mars is a cold world. The average surface temperature is about minus 60 degrees Celsius, similar to Antarctica in winter. But it's the extremes that are truly remarkable. Near the equator during summer, midday temperatures can climb to a relatively pleasant 20 degrees Celsius. You could almost imagine being comfortable, if not for the lack of breathable atmosphere. But at night in that same location, temperatures plunge to minus 70 or even 80 degrees Celsius. Near the poles in winter, it gets even colder, down to minus 125 degrees Celsius or lower. These temperature swings, from above freezing to far below zero and back again within a single Martian day, would stress any equipment or structure. Materials expand and contract, seals crack, mechanical components fail. Maintaining a habitat in these conditions requires constant vigilance and robust engineering. Every connection, every seal, every window or airlock represents a potential failure point where the cold or the vacuum could intrude. The lack of liquid water on Mars's surface is a direct consequence of the low pressure and temperature. While Mars has abundant water, it exists almost entirely as ice, locked in the polar caps and buried in the soil at higher latitudes. There's water vapor in the atmosphere, but the air is so thin and the temperature so low that the atmosphere is effectively saturated at very low absolute humidity. Morning frosts of carbon dioxide and water ice can form on the surface in some regions, but they sublime back into the atmosphere as the sun rises. Mars has no ozone layer to filter ultraviolet radiation from the sun. On Earth, ozone in the stratosphere absorbs most of the sun's harmful UVB and UVC radiation. On Mars, with no ozone and minimal atmosphere, UV radiation reaches the surface at levels much higher than Earth's, high enough to damage plastics, degrade organic materials, and harm living tissue. Astronauts would need UV protective visors on their helmets. Solar panels would need special coatings. Any exposed organic materials, whether biological tissue or plastic components, would deteriorate over time. Then there are the dust storms. Mars is famous for its dust storms, some of which can grow to envelope the entire planet for weeks or months at a time. The dust is incredibly fine, particles much smaller than beach sand, easily lofted into the thin atmosphere by winds that can reach speeds of 60 to 100 kilometers per hour or more. While these winds don't have the force of Earth's hurricanes because the atmosphere is so thin, they can still cause problems. Dust coats everything. It gets into mechanical systems, clogs filters, and covers solar panels, reducing their power output dramatically. The 2018 global dust storm on Mars ended the Opportunity rover's mission when dust blocked so much sunlight that the rover's solar panels could no longer generate sufficient power. A human habitat would face similar challenges. Solar panels would need regular cleaning, a task requiring human effort in a hostile environment. Air filtration systems would work over time to keep dust out of habitats, and even small amounts of dust inside could pose health risks if inhaled. The dust itself is another hazard. Martian soil contains perchlorates, chlorine-based compounds that are toxic to humans and can damage the thyroid gland and interfere with metabolism. Every time astronauts return from a surface excursion, they had to bring traces of this dust with them, requiring careful decontamination procedures to prevent it from accumulating inside living spaces. Studies simulating long-term exposure to Martian dust analog materials have raised concerns about respiratory damage and other health effects. Water extraction would be one of the most critical and challenging tasks for a Mars mission. While we know water ice exists beneath the Martian surface, accessing it isn't simple. At lower latitudes near the equator, where temperatures are more moderate and solar power more reliable, water ice may be buried meters beneath the surface, requiring drilling and excavation. The ice-rich layers in these regions are thought to be leftovers from ancient climate cycles, now buried under protective layers of dust and rock. At higher latitudes, water ice is more accessible, sometimes just centimeters below the surface, but the environment is harsher. Temperatures are colder, reducing the efficiency of equipment and increasing heating requirements. Solar power is less reliable due to lower sun angles and longer periods of darkness during winter. NASA's Phoenix lander in 2008 successfully confirmed the presence of water ice just beneath the surface at 68 degrees north latitude. But operating in that environment proved challenging even for the short-lived robotic mission. Extracting water from the Martian soil, whether from ice-rich permafrost or from hydrated minerals that contain water locked in their crystalline structure, requires significant energy. You'd need to excavate the soil, heat it to release the water through sublimation or dehydration, capture the water vapor, and purify it. Every step requires equipment that must function reliably in the Martian environment. drilling equipment must operate in extremely cold temperatures and handle soil that can be harder than concrete when frozen. Heating systems must work efficiently to minimize power consumption. Then there's the challenge of the Martian day. A sol, as it's called, is 24 hours, 39 minutes, and 35 seconds long, remarkably close to Earth's 24-hour day. This is one of the few environmental factors on Mars that's actually helpful for humans. Our circadian rhythms, our internal biological clocks, naturally run on roughly a 24-hour cycle. Adapting to a Martian sol wouldn't be particularly difficult physiologically. But the Martian year is 687 Earth days, about 669 Martian sols. Because Mars's axis is tilted at about 25 degrees, similar to Earth's 23.5 degrees, Mars experiences seasons like Earth does. However, these seasons are about twice as long as Earth's. A Martian summer near the equator lasts several Earth months, as does winter. This has implications for solar power, temperature extremes, and atmospheric dynamics, including the dust storm seasons that occur during certain parts of the Martian year. The lack of a global magnetic field on Mars, mentioned earlier in the context of radiation, has broader environmental implications. Without a magnetic field to protect it, Mars's thin atmosphere is constantly being stripped away by the solar wind. This is a slow process on human timescales, but over billions of years, it transformed Mars from a world that may have once had an atmosphere thick enough to support liquid water and possibly life into the dry, cold desert we see today. For future Mars settlers, this means that any attempt to terraform Mars, to deliberately thicken its atmosphere and warm the planet, would face the challenge of atmospheric loss. Without a magnetic field, any atmosphere created would gradually be lost to space. Living in this environment means accepting that you can never go outside without a full pressure suit. There are no afternoon strolls in the Martian countryside, no feeling the breeze on your face or the sun on your skin. The simple pleasures of being outdoors on Earth, the sensory connection to the natural world, don't exist on Mars in the way we know them. You're always separated from the environment by layers of technology. The walls of your habitat, the suit you must wear, the helmet over your face. Habitats would need to be more than just shelters. They'd need to be complete life support systems, maintaining breathable air, comfortable temperature and humidity, adequate pressure, and protection from radiation. They'd need to recycle water and air with very high efficiency because resupply from Earth would be impossibly expensive. They'd need redundant systems for every critical function because there's no quick rescue if something fails. Given the choice between living in such conditions indefinitely versus attempting a return journey through the radiation environment of space, consuming precious resources, and risking failure of aged equipment or ISRU systems, many astronauts might reasonably choose to stay. The Martian environment is harsh, but it becomes familiar. Habitats can be improved over time. More resources can be extracted. Underground facilities could provide better protection from radiation and temperature extremes. The challenges are known and can be addressed with time and effort. The return journey, by contrast, represents stepping back into the unknown. After months or years on Mars, exposure to the much higher radiation environment of the transit back to Earth could push cumulative doses beyond safe limits. Equipment that's been sitting unused on Mars may have degraded. The resources consumed during the return transit can't be used to improve life on Mars or support future arrivals. The alien environment of Mars is one more factor in the equation that makes one-way missions more practical than round trips. It's not insurmountable. Humans could live there indefinitely with the right technology. But it's sufficiently challenging that establishing a presence there consumes enormous resources and effort. Adding the complexity of a return mission on top of the already substantial challenge of surviving on Mars may simply be asking too much. Better, perhaps, to focus all resources and attention on making the one-way journey successful, on building a sustainable presence that can grow and evolve, than to split efforts between survival and planning for a departure that may never come. Section 5. The Body in Alien Gravity. Let your body relax now as we consider how it would change on a different world. Feel the weight of your body sinking into whatever surface supports you. That weight, that sensation of being pulled downward, is Earth's gravity at work. It's been shaping your body since before you were born, influencing how your bones grow, how your muscles develop, how your cardiovascular system distributes blood throughout your body. Gravity is so fundamental to your physiology that you never think about it, like breathing or the beating of your heart. But what happens when that fundamental force changes? On Mars, gravity is only 38% as strong as Earth's. If you weigh 70 kilograms on Earth, you'd weigh just 26.5 kilograms on Mars. At first, this might seem like a wonderful gift. You'd feel lighter, more agile. Jumping would take you 3 times higher. Lifting heavy objects would require far less effort. But your body, evolved over millions of years under Earth's gravity, would not appreciate this change. The human skeleton is a marvel of engineering, constantly building and rebuilding itself in response to the loads placed on it. Bone is living tissue, and it adapts to stress. When you walk, run, or lift heavy objects, specialized cells called osteocytes sense the stress and strain in your bones. This triggers a carefully orchestrated process. Cells, called osteoclasts, break down old or damaged bone tissue, while other cells, called osteoblasts, build new bone to replace it. Under normal circumstances on Earth, these processes balance, maintaining bone density and strength. But in reduced gravity, this balance breaks down. The loads on your skeleton decrease dramatically. Your bones no longer need to support as much weight. The osteocytes, sensing less stress, signal that the bones don't need to be as strong. The osteoclasts continue breaking down bone at their normal pace, but the osteoblasts slow down. Breakdown outpaces rebuilding, and bone density begins to decrease. On the International Space Station, where astronauts experience microgravity, near weightlessness, bone loss occurs at about 1 to 2% per month for weight-bearing bones like the legs, hips, and spine. This is alarming because it's roughly equivalent to 10 to 20 times the rate of bone loss in postmenopausal osteoporosis on Earth. After 6 months in space, astronauts can lose 10 to 15% of their bone mass in critical load-bearing bones. Mars, with its partial gravity, would likely cause bone loss as well, though probably at a slower rate than microgravity. Researchers don't yet have precise data for how partial gravity affects bone density, because we haven't had humans living in partial gravity for extended periods. Studies using animal models in centrifuges designed to simulate partial gravity suggest that bone loss would still occur, though perhaps at half the rate seen in microgravity. Even at half the rate, though, after a year on Mars, you could lose 5 to 7% of your bone mass. After several years, bone density could decline to levels that significantly increase fracture risk. Can this bone loss be prevented? On the International Space Station, astronauts spend about 2 hours every day exercising using specially designed equipment, resistance machines that simulate weightlifting, treadmills with harnesses that pull astronauts down to simulate body weight. These exercise protocols help reduce bone loss, but don't eliminate it entirely. Some astronauts still lose significant bone density, despite rigorous exercise regimens. On Mars, astronauts would have the advantage of the partial gravity itself, providing some loading on the skeleton. But whether 3/8 of Earth's gravity is enough to maintain bone health over years or decades remains an open question. Research suggests that there may be a threshold level of gravity needed to prevent bone loss, possibly around 40 to 50% of Earth's gravity. If Mars's 38% gravity falls below this threshold, long-term residents might experience progressive bone loss even with extensive exercise. The implications are profound. Weakened bones increase the risk of fractures from even minor accidents. On Mars, a broken bone isn't just a painful inconvenience. It's a potentially life-threatening emergency. Medical facilities would be limited. Emergency evacuation to Earth isn't possible. A serious fracture, particularly of the spine or pelvis, could leave someone incapacitated for weeks or months, consuming medical resources and potentially preventing them from contributing to the colony's survival. Even more concerning is what this means for the possibility of return. After years on Mars, an astronaut's bones may have become so weakened that they couldn't withstand the much stronger gravity of Earth. The return journey itself, with periods of acceleration and deceleration, could stress weakened bones. But the real challenge comes upon arrival at Earth. After years in partial gravity, attempting to walk around under Earth's full gravity could result in fractures. The astronaut's skeleton, adapted to Martian conditions, might literally be too weak to support their own body weight on Earth. Some astronauts returning from the International Space Station after 6-month missions have required months of rehabilitation to regain bone density and strength. Their bones are so weakened that they were at high risk of fracture during the first weeks back on Earth. Imagine this problem amplified by years instead of months, and compounded by the radiation exposure and other stresses of the Mars journey. Return might not just be difficult, it might be physiologically impossible. Muscle follows a similar pattern to bone. Without the constant loading of Earth's gravity, muscles atrophy, shrinking in size and losing strength. Studies of astronauts have shown that muscle mass can decrease by up to 20% in the legs after just a few weeks in microgravity, with strength declining even more, up to 30% or more. The muscles most affected are those we use to maintain posture and move around on Earth: the calves, thighs, back, and core muscles. On Mars, again, the partial gravity provides some benefit compared to microgravity, but it's unclear whether it's enough. The lower gravitational load means that simply moving around on Mars requires less muscular effort than on Earth. Over time, without deliberate exercise to maintain strength, muscles would adapt to the Martian environment by getting smaller and weaker. This might not be problematic for living on Mars long term. You'd be adapted to the environment you're in. But it could make return to Earth extremely difficult or impossible. The cardiovascular system is also affected by altered gravity. On Earth, your heart must pump blood upward against gravity to reach your brain when you're standing. Your leg muscles help by squeezing veins and pushing blood back toward the heart. The cardiovascular system is finely tuned to Earth's gravity. In microgravity, fluids in the body redistribute. moving from the legs toward the head and chest. Astronauts often report feeling congested, like having a head cold. The heart doesn't have to work as hard against gravity, so it deconditions over time, becoming less efficient. When astronauts return to Earth, they often experience orthostatic intolerance, difficulty maintaining blood pressure when standing, which can lead to dizziness or fainting. On Mars, these effects would be less severe than in microgravity, but still present. The heart wouldn't have to work against as much gravity, potentially leading to some level of deconditioning. The magnitude of these changes and whether they would prevent return to Earth is unknown, but they add to the cumulative burden of physiological changes that make one-way missions more practical than round trips. There are also concerns about cellular and molecular changes in reduced gravity. Research has shown that gravity helps cells organize their internal structures. Microtubules, protein filaments that give cells their shape and help organize cellular machinery, may not form correctly in reduced gravity. This could affect how cells divide, how they respond to damage, how they communicate with each other. The long-term consequences of these cellular-level changes are poorly understood, but they could potentially affect everything from wound healing to the risk of cancer. The nervous system, too, may be affected. Studies of astronauts have shown changes in vision, possibly due to increased intracranial pressure from fluid redistribution. Some astronauts have developed swelling of the optic nerve and flattening of the eyeball, leading to changes in vision that can persist after returning to Earth. The exact mechanisms aren't fully understood, but it's another example of how the human body, evolved for Earth's environment, responds in unexpected ways to altered gravity. All these physiological changes, bone loss, muscle atrophy, cardiovascular deconditioning, and cellular-level alterations accumulate over time. Each month, each year on Mars, an astronaut's body becomes more adapted to Martian gravity and less suited to Earth's. There may come a point, perhaps after just a few years, where the physiological changes are so extensive that return to Earth would be medically impossible or inadvisable. The body would have become, in effect, Martian. This creates an interesting paradox. The longer astronauts stay on Mars, the more they accomplish, the better they adapt to the environment. The more they learn, the less likely it becomes that they could ever come home. Success in the mission, measured by effective long-term presence and productivity on Mars, ensures that the mission becomes permanently one way. This isn't a failure. It's the natural consequence of human physiology adapting to a new gravitational environment. Rather than fighting against this reality, perhaps we should accept it. A mission designed from the start as one way can focus resources on ensuring the health and well-being of astronauts in the Martian environment, rather than trying to maintain their ability to return to Earth. Exercise regimens can be optimized for Mars, not for Earth return. Medical planning can focus on Mars-specific health challenges. Habitats can be designed for permanent, multi-generational occupation rather than temporary presence. The human body's response to Martian gravity is yet another factor pointing toward the practical necessity of one-way missions. Our biology, shaped by billions of years of evolution under Earth's gravity, doesn't easily adapt to other worlds. The changes that occur in reduced gravity may be irreversible beyond a certain point. Rather than viewing this as a limitation, perhaps we should see it as an opportunity, the chance to become the first truly Martian humans, adapted to their new world in ways both wonderful and profound. Section 6. The Isolation Factor. Picture yourself in a small enclosed space with a handful of other people. You cannot leave. You cannot open a window to feel fresh air. You cannot take a walk in nature or visit friends who live elsewhere. Every face you see is one of the same few faces you've seen every day for months. Every voice you hear is familiar to the point of tedium. The walls are always the same. The sounds, the smells, even the quality of light, all unchanging. Now imagine that this situation will continue not for weeks or months, but for years, possibly forever. This is the psychological reality of a Mars mission. The isolation, the confinement, the permanence of the situation. These create mental and emotional challenges that are as significant as the physical hazards of radiation or bone loss. Human beings are social creatures. We evolved in groups, tribes, communities. We need social interaction, novelty, the ability to retreat to private space when we need solitude, contact with nature, changes of scene, and stimulation. A Mars mission deprives astronauts of most of these fundamental psychological needs. The journey to Mars takes 6 to 9 months, depending on the alignment of the planets and the propulsion system used. During this time, the crew lives in a spacecraft that's likely no larger than a small apartment. NASA's current designs call for habitats around 50 to 100 cubic meters of livable space, about the size of a studio apartment, for a crew of 4 to 6 people. Imagine sharing that studio apartment with 5 other people for the better part of a year, with no opportunity to leave, no privacy beyond perhaps a curtain around your sleeping area, no fresh food, no nature, nothing but the constant hum of life support systems and the faces of your crewmates. Studies of long-duration space missions and analogs on Earth have identified numerous psychological challenges. Crews report tension and conflicts between members, often over trivial matters that become magnified in the confined environment. Sleep patterns are disrupted by the stress, the unusual environment, the lack of natural day-night cycles in space. Mood disorders, particularly depression and anxiety, can emerge. Cognitive performance, the ability to concentrate, make decisions, solve problems, can decline. The Mars 500 experiment, conducted by Russia's Institute of Biomedical Problems, simulated a complete Mars mission by confining 6 men in a mock spacecraft in Moscow for 520 days, from June 2010 to November 2011. This was the highest fidelity simulation of a Mars mission ever conducted on Earth. While the crew was never in actual danger and knew they could be extracted in an emergency, the psychological environment was as close to a real Mars mission as possible without leaving Earth. The results were revealing. The crew showed substantial inter-individual differences in how they coped with the confinement. Some members remained psychologically resilient throughout, maintaining good mood, normal sleep, and high performance on cognitive tests. Others struggled significantly, showing signs of depression, fatigue, disturbed sleep patterns, and decreased motivation. One crew member became significantly more sedentary as the mission progressed, moving less and sleeping more, possibly as a way of psychologically withdrawing from the stressful environment. Importantly, the Mars 500 crew knew this was a simulation. They knew that it would end. They knew that emergency extraction was possible if absolutely necessary. Real Mars astronauts wouldn't have these psychological safety nets. The isolation would be absolute. There is no possibility of rescue or early return. If conflicts arise that make the social environment unbearable, there's no escape. If someone develops severe depression or other psychiatric symptoms, the resources available to help are limited to what was brought from Earth and the skills of other crew members. Communication with Earth provides some relief from isolation, but also creates its own challenges. Due to the vast distance between Earth and Mars, radio signals traveling at the speed of light take between 3 and 22 minutes to make the one-way trip, depending on where Earth and Mars are in their orbits. This means communication delays range from 6 to 44 minutes for a round-trip exchange. Real-time conversation is impossible. Phone calls with loved ones become an exchange of messages with long pauses in between. This communication delay has profound psychological implications. When someone is struggling emotionally, when they need support or advice, they can't have a live conversation with a counselor or loved one on Earth. They must record their message, wait the 20 minutes or more for it to reach Earth, and for the response to come back. By the time the reply arrives, the crisis may have evolved or resolved, leaving the astronaut to cope largely on their own. Mission Control can't provide real-time guidance for emergencies. If equipment fails, if a medical crisis occurs, if a critical decision needs to be made, the crew must handle it themselves. The psychological burden of this level of autonomy and responsibility is immense. There's no one to turn to for immediate help, no authority figure to take control in a crisis. The crew must be entirely self-sufficient. Research on Antarctic winter overcruise provides some insight into extended isolation in extreme environments. Antarctica bases during winter are as isolated as humans can be on Earth. The crew can't leave. Supply ships can't arrive. Medical evacuation is often impossible. Radio communication is available but limited. Psychological studies of these crews have found what's called the third quarter phenomenon, a period typically occurring about 3/4 of the way through the isolation where mood significantly deteriorates, conflicts increase, and performance declines. People start to feel that the situation is endless, that they've been isolated forever and will be isolated forever. For a Mars mission, this third quarter phenomenon could occur during the journey itself, or during the time on Mars, or during the return trip if there is one. But here's a crucial difference. Antarctic crews know when the winter will end. They have a fixed date when the isolation terminates. Mars astronauts on a one-way mission don't have that psychological anchor. The isolation is permanent. How does the human psyche cope with permanent isolation from Earth, from the billions of other humans, from everything familiar? One possible source of psychological support is the overview effect, a shift in perspective that astronauts report when seeing Earth from space. Many describe feeling a profound sense of connection to the planet, to all life on it, to all of humanity. They report that the petty divisions and conflicts that dominate life on Earth seem trivial when viewed from space. This can be a powerful, positive, psychological experience. But from Mars, Earth appears as just a bright star in the sky, indistinguishable to the naked eye from Venus. The overview effect might transform into what some researchers call the Earth out of view phenomenon, a profound sense of isolation and disconnection from humanity. Instead of feeling connected to Earth, Mars astronauts might feel utterly alien, separated from the only world where human life exists by millions of kilometers of empty space. Screening and training can help select astronauts who are psychologically suited to the challenges of long-duration spaceflight. Current astronaut selection processes include extensive psychological evaluation, looking for traits like resilience, adaptability, emotional stability, and the ability to work effectively in teams under stress. Training includes simulations, team-building exercises, and practice in confined environments. But there's only so much that selection and training can accomplish. The psychological stress of a multi-year or permanent Mars mission is unprecedented in human experience. We don't know how even the most psychologically resilient individuals will respond. Some might thrive, finding the challenge invigorating and meaningful. Others might struggle profoundly, developing psychiatric symptoms that could threaten both their own well-being and the mission's success. The composition of the crew becomes critically important. Cultural differences, language barriers, personality clashes, all can be amplified in confined isolation. Previous space missions have experienced significant interpersonal tensions. Russian cosmonauts and American astronauts have sometimes had difficulties working together due to different training approaches, communication styles, and organizational cultures. All male crews have shown different social dynamics than mixed-gender crews. The ideal crew composition for a long-duration Mars mission is still a subject of research and debate. Privacy, or rather the lack of it, is another major challenge. In the confined space of a Mars habitat or transit vehicle, true privacy is almost impossible. You're always aware of where your crewmates are, what they're doing, what they're saying. Personal space is minimal. The psychological need for solitude, for time alone to process thoughts and emotions, is difficult to satisfy. Some designs for Mars habitats include small private quarters for crew members, but these would likely be barely larger than a closet, just enough room for a bed and perhaps a small desk. The psychological challenge extends beyond the crew themselves to their relationships with people on Earth. Spouses, children, parents, friends, all must cope with the knowledge that their loved one is on another planet and may never return. The communication delays mean that these relationships become asynchronous, more like writing letters than having conversations. Over time, the psychological distance might grow to match the physical distance. Crew members might find themselves feeling more connection to their fellow Martians than to people on Earth. This psychological transformation, the shift from identifying as an Earthling to identifying as a Martian, might be necessary for long-term mental health on Mars. If you're constantly longing to return to Earth, constantly mourning what you've lost, the psychological burden could become unbearable. But if you can shift your identity, if you can come to see Mars as your home and your crew as your primary community, if you can find meaning and purpose in the mission itself, the psychological challenge becomes more manageable. This is perhaps another argument for the one-way nature of Mars missions. If return is impossible, if everyone involved knows from the start that this is a permanent relocation, the psychological adaptation might actually be easier. There's no false hope, no waiting for a return that may never come. No ambiguity about whether you're a visitor or a resident. You are Martian. This is your home. The psychological clarity of that might be healthier than the uncertainty of a mission with an unclear or unlikely return. The isolation factor is one of the most challenging and least understood aspects of Mars exploration. Unlike radiation, which we can measure and model, unlike fuel requirements, which we can calculate precisely, the human psychological response to extreme isolation and confinement is variable and unpredictable. We can prepare, we can select crew carefully, we can provide support and resources, but ultimately, we won't know how people will cope until they're actually there. living the reality of being the most isolated humans in history. And, given the challenges of return, that isolation may need to become permanent for the mission to succeed. Section 7. Making Mars Home. ISRU and Survival. Let yourself breathe deeply now and imagine what it means to truly live on another world. Not to visit, not to explore briefly and return, but to make an alien planet your home. Every resource you need to survive must be created, extracted, or transformed from the materials around you. Every breath of air, every drop of water, every calorie of food, all must come from Mars itself or from carefully managed recycling systems. This is the reality of in situ resource utilization, or ISRU, and it's both the greatest challenge and the strongest argument for why Mars missions may need to be one way. ISRU is the concept of using local resources to support human presence in space. Instead of bringing everything from Earth, which is prohibitively expensive and limited by the mass you can launch, you extract and process materials where you are. For a Mars mission, ISRU isn't just a nice-to-have feature that reduces costs. It's absolutely essential for long-term survival. The most critical resource is water. Humans need about 2 to 3 liters of water per day for drinking, more for food preparation, hygiene, and other uses. A crew of 6 people would need at least 4,000 liters of water per year just for drinking and cooking, more if you include water for growing food, washing clothes, and showering. Bringing this water from Earth is impractical. Water is heavy. 1 liter equals 1 kilogram, and the transportation costs are staggering. Therefore, water must be obtained on Mars. Fortunately, Mars has water. The polar ice caps contain vast amounts of water ice mixed with frozen carbon dioxide. Radar observations from orbiting spacecraft have revealed massive deposits of nearly pure water ice at high latitudes, sometimes just meters below the surface. Even near the equator, where temperatures are more moderate, there's evidence of water locked in minerals and perhaps as deeper deposits of ice left over from different climate conditions in Mars's past. But extracting this water isn't simple. At high latitudes where ice is most accessible, the environment is harsh. Temperatures are colder, averaging minus 60 degrees Celsius or lower, with winter temperatures plunging below minus 100 degrees. Solar power is less effective due to lower sun angles and long winter nights. Nuclear power would likely be necessary for reliable year-round operation. The extraction process might involve drilling to reach the ice layer, then using heat to sublime the ice directly from solid to vapor, skipping the liquid phase because of the low atmospheric pressure. The water vapor would be captured, condensed, and purified. Alternatively, ice-rich soil could be excavated, brought into a processing facility, heated to release the water, which is then collected and purified. Each approach requires substantial energy, mining, or drilling equipment that can operate in Martian conditions, and processing, systems that won't freeze or fail in the extreme environment. NASA's MOXIE experiment aboard the Perseverance rover has demonstrated another crucial ISRU capability, producing oxygen from the Martian atmosphere. MOXIE, which stands for Mars Oxygen In Situ Resource Utilization Experiment, uses a process called solid oxide electrolysis to split carbon dioxide molecules from the Martian atmosphere into oxygen and carbon monoxide. Over the course of its operation, MOXIE successfully produced oxygen in multiple runs, proving that the technology works in actual Martian conditions. Scaling this up to produce the amount of oxygen needed for human breathing and potentially for rocket propellant is technically feasible, but requires significant infrastructure. A full-scale system would need to compress Martian atmosphere, feed it through electrolysis units heated to about 800 degrees Celsius, separate and store the oxygen, and safely vent or use the carbon monoxide byproduct. The system would need kilowatts of electrical power operating continuously. Oxygen for breathing is only part of the equation. Humans also need nitrogen to dilute the oxygen, preventing the fire hazard of pure oxygen atmospheres and providing the nitrogen that plants need to synthesize proteins and other biological molecules. Mars's atmosphere is about 2.7% nitrogen, so it can be extracted from the atmosphere, but the process requires separating it from the much more abundant carbon dioxide. This adds another layer of complexity to the ISRU systems. Food production is perhaps the most challenging ISRU problem. Humans need roughly 2,000 to 2,500 calories per day, along with adequate protein, vitamins, minerals, and fiber. Bringing enough food from Earth for a multi-year mission or permanent settlement would require enormous mass. Therefore, growing food on Mars is essential for long-term sustainability. Growing plants on Mars faces multiple challenges. The Martian soil, while rich in many minerals, lacks the organic matter and nitrogen compounds that plants need. It contains toxic perchlorates that would need to be removed or neutralized. The low atmospheric pressure means that greenhouses would need to be pressurized and sealed. The weaker sunlight means that supplemental lighting might be necessary, consuming precious power. The lower gravity might affect how plants grow, though studies on the International Space Station suggest that plants can grow reasonably well in reduced gravity with proper care. Proposed solutions include hydroponic or aeroponic systems, where plants grow in water or mist with dissolved nutrients rather than soil. This allows better control over the nutrients, avoids the perchlorate problem, and uses water more efficiently. But it requires infrastructure, tanks, pumps, lights, climate control systems, and a reliable power source. The knowledge and labor required to maintain these systems shouldn't be underestimated. Growing food isn't just a matter of planting seeds. It's an ongoing process requiring daily attention, skills in agriculture and biology, and the ability to troubleshoot problems when crops fail or systems malfunction. Energy production is fundamental to all other ISRU activities. Without reliable power, you can't extract water, produce oxygen, grow food, maintain habitat temperature, or run any of the other systems necessary for survival. Solar power is the obvious choice on Mars. The planet receives about 43% the sunlight that Earth does at the equator, which is still substantial, comparable to parts of northern Europe. Modern solar panels can function effectively in these conditions. However, solar power on Mars faces challenges. Dust storms can reduce sunlight dramatically, sometimes for weeks at a time. Dust accumulation on solar panels reduces their efficiency unless regularly cleaned, which requires either human labor outside the habitat or robotic cleaning systems. Seasonal and daily variations in sunlight mean you need energy storage, batteries, or other systems to provide power during the night and during winter, at higher latitudes when days are shorter. Nuclear power provides an alternative. A small nuclear reactor could provide steady, reliable power regardless of dust storms or darkness. NASA has developed kilopower reactors designed specifically for space missions, capable of providing several kilowatts of electrical power continuously for years. But nuclear reactors are politically sensitive, complicated to design and operate safely, and represent a single point of failure if something goes wrong. Most likely, Mars settlements would use a combination of power sources: solar panels for baseline power during favorable conditions, supplemented by nuclear reactors for reliability and for high-latitude locations or operations during dust storms or winter. Battery systems would provide short-term storage and load balancing. All these ISRU systems, water, extraction, oxygen production, food growing, power generation, represent enormous infrastructure that must be established before a permanent human presence is viable. Some of this infrastructure would need to be sent from Earth and set up robotically before the first crew arrives. Other systems could be expanded and improved by subsequent crews. But each piece of infrastructure represents mass that must be launched from Earth, equipment that must survive the journey and operate in Martian conditions, and complexity that increases the risk of failure. Here's where the one-way nature of Mars missions becomes almost inevitable. Every kilogram of mass, every watt of power, every square meter of greenhouse space that you dedicate to ISRU infrastructure is a resource that supports permanent settlement but doesn't contribute to a return journey. If you're trying to maintain the option for return, you need to balance ISRU resources between supporting the crew on Mars and producing propellant for the return journey. This creates conflicts and inefficiencies. Fuel production for a return rocket requires vast amounts of resources. Remember that 30 to 33 metric tons of methane and liquid oxygen are needed. Producing this through ISRU would require large-scale chemical processing plants, likely extracting water from ice and reacting it with atmospheric carbon dioxide through the Sabatier process. This requires significant power, perhaps 50 to 100 kilowatts operating for months, and substantial processing equipment. If that same power and equipment were instead used for life support, for growing food, for producing materials for habitat expansion, the settlement would be more robust, more comfortable, more likely to survive and thrive. The resources needed to maintain the option of return are substantial enough that they could meaningfully improve the quality of life and probability of success for a permanent settlement. There's also the question of time horizons. ISRU systems need months or years to produce significant quantities of resources. A return mission has a fixed timeline. You need the fuel ready by a specific departure window when Earth and Mars are properly aligned for efficient transit. If the ISRU systems don't produce enough fuel in time, the mission is scrubbed or delayed, or astronauts are stranded. The pressure and risk associated with this timeline are enormous. A permanent settlement has more flexibility. If crop yields are lower than expected one year, the settlement can adjust, perhaps supplementing with stored food or reducing consumption until the next harvest. If water extraction proceeds slower than planned, the settlement can prioritize its use and gradually expand capacity. The timeline is determined by needs and capabilities, not by orbital mechanics. Furthermore, ISRU systems become more efficient and effective over time as crews learn how to operate them in actual Martian conditions, as equipment is maintained and upgraded, as new techniques are discovered. A permanent settlement can invest in ISRU infrastructure with the knowledge that it will be used and improved for decades. A short-term visit or a return mission doesn't have time to fully develop and optimize these systems. The expertise required for ISRU operations is another factor. Crews would need skills in chemistry, biology, engineering, geology, agriculture, and more. Training someone to operate all these systems takes time and sustained practice. For a permanent settlement, crews can specialize, with some becoming expert water extraction engineers, others agricultural specialists, others power systems managers. For a short-term return mission, the crew needs to be generalists, able to do a little bit of everything, but perhaps not truly expert in any one area. The success of ISRU is what makes long-term human presence on Mars possible, but it's also what makes return increasingly difficult and unnecessary. Once you've invested the resources to establish a functioning ISRU infrastructure, once you've trained crews to operate and maintain it, once you've created a sustainable life support cycle extracting resources from Mars, you've created the conditions for a permanent settlement. The settlement becomes, in a sense, self-reinforcing. Success in ISRU makes the settlement viable, and the viability of the settlement justifies continued investment in ISRU. Return, at that point, starts to look like abandoning success. You've built something that works. Why dismantle it or leave it behind? The resources used to fuel a return journey could instead expand the settlement, support more people, increase redundancy and resilience. The human capital, the skills and knowledge that crews have developed, is more valuable on Mars where they can apply it than on Earth, where it becomes merely historical experience. This is perhaps the strongest practical argument for one-way Mars missions. ISRU creates the conditions for permanent settlement, and permanent settlement makes the investment in ISRU worthwhile. The two concepts reinforce each other. Trying to maintain both ISRU for settlement and propellant production for return creates conflicts in resource allocation and reduces the probability of success for both objectives. Better to commit fully to one path, to embrace the reality that we're creating a new branch of humanity on Mars, than to hedge and compromise and risk achieving neither goal fully. Section 8. The point of no return. There comes a moment in every journey when turning back becomes impossible. For a hiker deep in the wilderness, it might be the point where the trail behind has become too dangerous to retrace. For a ship at sea, it's when fuel and supplies are insufficient for the return voyage. For astronauts heading to Mars, the point of no return isn't a single moment, but rather an accumulation of factors, each one making return a little more difficult, a little less likely, until the sum total makes it effectively impossible. Let's trace this progression, understanding how a Mars mission transitions from theoretically round trip to practically one way. The journey begins on Earth with launch. From this moment, the crew has committed to at least the outbound journey. The spacecraft accelerates away from Earth, reaching the velocity needed to escape Earth's gravity and head toward Mars. After a few hours or days, turning around becomes impractical. The fuel required to reverse course, return to Earth, and land safely would be enormous. The mission has crossed its first point of no return. During the 6 to 9 month transit to Mars, the crew accumulates radiation exposure. Remember that studies suggest the round-trip journey alone would expose astronauts to about 60% of their career radiation limit. By the time the spacecraft reaches Mars, the crew has already absorbed 30% or more of this total. They're already a third of the way toward the maximum radiation they can safely receive in their careers. Every additional day in space or on Mars adds to this total. If at this point, before landing on Mars, the crew turned around and immediately headed home, They'd arrive back at Earth having exceeded safe radiation exposure limits, but possibly not to a degree that guarantees serious health consequences. The return would be difficult and risky, but physiologically possible. However, turning around before landing would mean abandoning the entire purpose of the mission. The science, the exploration, the establishment of infrastructure, all the objectives that justified the enormous expense and effort would be lost. No mission planner would design for such a contingency. The crew would land on Mars. Landing on Mars requires consuming propellant. The spacecraft must slow from interplanetary cruise velocity, enter Mars's atmosphere, use the thin atmosphere for some braking through aerodynamic heating, and then fire rockets to achieve a controlled landing. This propellant is gone, used up. If the mission hasn't pre-positioned return fuel on Mars through ISRU or cached supplies, the crew is now stranded, at least temporarily. They must either produce return fuel on Mars or accept that they're staying. The time on Mars's surface is where the physiological changes really accumulate. Bone density decreases by perhaps 1 to 2% per month. Muscles atrophy, adapting to the lower gravity. The cardiovascular system deconditions. Radiation exposure continues, somewhat reduced from the space environment but still well above Earth levels. Each month on Mars makes the crew's bodies less suited to Earth's environment, and potentially less capable of surviving the return journey. Psychological changes occur as well. The crew adapts to the Martian environment, to the rhythms of Martian days, to the society of their small group. Relationships with people on Earth become more distant, more abstract. Communication delays and the lack of shared experience create a psychological gap. The crew might begin to identify more strongly with their fellow Martians than with Earth's billions. If the mission plan includes ISRU production of return propellant, this process takes months or years. Systems must be set up, tested, and operated to extract water, produce methane and oxygen, and store the propellant at cryogenic temperatures. All this infrastructure works toward the goal of enabling return, but it also represents investment in Mars. The habitats, the life support systems, the food production, the power generation, all become more developed, more capable, more comfortable. Here's a thought experiment. Imagine the crew has been on Mars for 2 years. They've successfully produced the propellant needed for return. The launch window to Earth is approaching, the period when orbital mechanics favor efficient transit. The spacecraft they arrived in has been sitting on Mars for 2 years, exposed to dust, radiation, and temperature cycling. It would need to be carefully inspected, systems tested and refurbished where necessary, to ensure it's capable of the return journey. The crew has lost perhaps 10 to 15% of their bone density. Their muscles have atrophied significantly. They've absorbed substantial additional radiation. Returning to Earth would expose them to another 30% or more of their career radiation limit during the transit. Upon arrival, they'd need months of rehabilitation to regain bone strength and adapt to Earth's gravity. Some might have developed health problems that would make this rehabilitation difficult or unsuccessful. Meanwhile, on Mars, they've built something meaningful. They've learned how to live there. They have crops growing, systems functioning, knowledge and skills that make them valuable to any future expansion of the settlement. They might have formed close bonds with their crewmates, relationships that feel more important than the increasingly distant connections to Earth. Faced with this choice, what would you do? Would you board that spacecraft, knowing the return journey is risky, that it will further damage your health, that you might arrive on Earth unable to walk, possibly unable to fully recover? Or would you stay on Mars, where you've adapted, where you're productive, where you're needed? This is the point of no return in its most profound sense. It's not that return is physically impossible. The rocket could still launch, the trajectory could be calculated, the spacecraft could make it back. But the cost in health, in risk, in abandoning a successful settlement might be too high to justify. The rational choice, the choice that maximizes the crew's long-term well-being and the mission's scientific and exploratory value, might be to stay. Now consider that mission planners, aware of all these factors, might design the mission from the start as one way. They'd eliminate the return propulsion system entirely, saving enormous mass. They'd optimize ISRU for settlement support rather than splitting resources with propellant production. They'd select crew members with the psychological profile suited to permanent settlement, people excited about the prospect of becoming Martian, rather than apprehensive about whether they can return. A one-way mission, designed as such from the beginning, could be more successful, safer in certain ways, and more cost-effective than a round-trip mission with an increasingly unlikely return component. The point of no return, instead of being a gradual accumulation during the mission, would be the moment the crew steps aboard the outbound spacecraft, knowingly and willingly committing to a one-way journey. This might seem like a grim prospect, asking astronauts to give up any hope of returning to Earth. But consider the historical precedent. Throughout human history, people have undertaken one-way journeys into the unknown. The Polynesians who sailed across the Pacific to settle new islands had no guarantee they'd ever see their home islands again. The Europeans who crossed the Atlantic to settle the Americas knew the journey was so arduous and expensive that few would ever return. The pioneers who traveled the Oregon Trail understood that they were leaving their old lives behind permanently. Were these people making a tragic sacrifice? Or were they making a courageous choice, pursuing opportunity, adventure, and the chance to build something new? Many letters and diaries from these historical migrants express not regret, but excitement, determination, and pride in what they were creating. The first Martians would be in a similar position. They'd be pioneers, knowing that they're undertaking a one-way journey but driven by the magnitude of what they're achieving. Becoming the first humans to live on another planet, establishing the foundation for a multiplanetary civilization, ensuring that human consciousness and culture extend beyond a single fragile world. The ethical considerations are complex. Is it morally acceptable to send people on a mission they can't return from? Most would argue yes, provided the astronauts fully understand the implications and consent freely. Astronauts already accept substantial risks. Every time someone boards a spacecraft, there's a chance they won't come back. Making that risk explicit and certain doesn't change the fundamental nature of the bargain between astronaut and space, agency, between explorer and society. What about the astronauts' families? How would they cope with knowing their loved one is on Mars permanently? This is where careful psychological support and preparation become essential. Families would need counseling, ongoing support, and the understanding that their astronaut is achieving something historic. Perhaps seeing images and messages from Mars, knowing that their loved one is thriving, contributing, being part of something larger than themselves would provide comfort. The point of no return for Mars missions isn't a failure of planning or technology. It's a recognition of reality. The factors that make Mars exploration challenging: radiation, fuel requirements, physiological changes, psychological adaptation, ISRU commitment, all push toward permanent settlement rather than temporary visits. Fighting against this reality would be like fighting against gravity, theoretically possible but practically foolish. Instead, we should embrace the reality. Design missions as one way from the start. Select crews who are excited about becoming Martian. Build settlements intended to grow and evolve over generations. Think of Mars not as a destination we visit, but as a new home we're creating. This shift in mindset transforms the challenge from how do we get there and back to how do we thrive there. That second question is more inspiring, more achievable, and more aligned with the ultimate goal of becoming a multiplanetary species. The point of no return for Mars is also a point of beginning. It's where we stop being solely Earthlings and start becoming something more. A species that lives on multiple worlds, that has branches on different planets, that is hedged against extinction by spreading beyond our cradle. That's worth the one-way journey. Conclusion. As we drift toward the end of our exploration tonight, let your mind settle, your breathing slow. We've journeyed through the realities of Mars exploration, understanding the challenges that make it one of the most ambitious endeavors humanity has ever contemplated. We've seen how radiation bombards travelers through the solar system, how the rocket equation demands exponential quantities of fuel, how the alien environment challenges every biological system, how the human body adapts in ways that make return increasingly difficult, how isolation tests the limits of psychological resilience, and how the commitment to in situ resource utilization creates the foundation for permanent settlement. Each of these factors alone presents a serious challenge. Together, they create a situation where the most practical, perhaps the only realistic approach to Mars exploration is to embrace the one-way nature of the journey. This might sound like a limitation, like settling for less than we hoped, but perhaps we should see it differently. The one-way journey to Mars is not a failure of technology or imagination. It's an opportunity to achieve something unprecedented, the establishment of a permanent human presence on another world. Every previous step in space exploration, from the first satellites to the International Space Station, has been about going out and coming back. Mars is where we finally stay. The courage required for such a mission is profound. The first Martians would be giving up Earth, the world that gave birth to all life we know of, the planet with its blue skies and green forests and vast oceans. They'd be leaving behind most of human civilization, all the art and culture and history that we've accumulated over millennia. They'd be committing to a harsh, alien world where survival requires constant effort and vigilance. But they'd also be gaining something unique. They'd be the founders of a new branch of humanity, the first Martians. Their names would be remembered for as long as human civilization exists. They'd have the opportunity to build a society from scratch, to learn lessons from Earth's history, and perhaps create something better. They'd experience sights and sensations no earthbound human could imagine. Watching Earth rise as a brilliant blue star, feeling the lighter gravity, seeing the twin moons Phobos and Deimos racing across the sky, exploring alien landscapes that have existed unchanged for billions of years. The children born on Mars, the first humans who've never known Earth except through stories and images, would be truly Martian. They'd think differently, adapted to a different gravity, a different day length, a different world. They'd represent the next step in human evolution, not through biological mutation but through adaptation to a new environment. This expansion to Mars is about more than just exploration or adventure. It's about ensuring the survival of human consciousness. Earth faces risks, asteroid impacts, supervolcano eruptions, nuclear war, climate change, pandemics, or dangers we haven't yet imagined. Any of these could threaten human civilization or even human existence. By establishing a self-sustaining presence on Mars, we create a backup, a second location for humanity that would survive even if Earth became temporarily or permanently uninhabitable. Mars also teaches us humility. The challenges of living there remind us how precious Earth is, how perfectly suited to life, how unusual in the cosmos. Every breath of air, every drop of clean water, every plant and animal, all the natural beauty and abundance of Earth. These are gifts we too often take for granted. Perhaps having humans on Mars, struggling to extract water from ice and grow food in pressurized greenhouses, will help those of us on Earth appreciate what we have and work harder to preserve it. The path to Mars won't be quick or easy. The technology needs further development. The costs are enormous. The risks are real and serious. It might be decades before the first humans set foot on Mars. But the dream is becoming more concrete, more achievable. Multiple space agencies and private companies are working toward this goal. Each robot rover on Mars, each test of ISRU technology, each long-duration mission to the International Space Station brings us closer to the day when Mars sees its first human footprints. When that day comes, when we watch images of humans walking on Mars, establishing habitats, planting the first crops, looking up at Earth in the Martian sky, we'll be witnessing something truly historic. We'll be watching humanity take its first permanent step off our homeworld. We'll be seeing the beginning of a multi-planetary civilization. And those first Martians, knowing they won't return to Earth, will look back at our pale blue dot and perhaps feel not regret but pride. Pride in their courage, in their contribution to human knowledge and survival, in the extraordinary thing they're achieving. They'll know that they're living the greatest adventure humans have ever undertaken. The journey to another world. The journey to make Mars home. So, as you drift off to sleep tonight, think about those future Martians. Think about the red deserts they'll explore, the discoveries they'll make, the civilization they'll build. Think about the human spirit that drives us to explore, to push boundaries, to seek out new worlds. And rest easy knowing that our species' future isn't limited to one fragile planet, but extends outward to the stars, starting with our neighbor Mars. Sleep well, and dream of red deserts and twin moons, of distant horizons and new beginnings, of the day when Mars stops being alien and starts being home. Thank you for joining me on this journey through the Science Pillow. Until next time, may your dreams be filled with wonder, and may you rest deeply.